All right. Hi, everyone. My name is Gilcrest, and I'm going to be sharing some thoughts on using folding in consumer-facing applications, specifically here at ZK Summit 11 with ZK Summit Folded. So, just jumping right into it, I'm not a math chat galaxy brain. This is all being done with very basic stuff. We're using Nova, which is essentially the most basic folding scheme available. And we're using CirCom, which is Nova Scotia, and I'll get into that. It's a really cool tool. But just really quickly, folded proofs themselves are not actually zero knowledge. All they are just incrementally verifiable computations saying that the sequential computations are constructed correctly. The way you actually get zero knowledge in a folding scheme, for instance Nova, is that you take something like Spartan and you wrap the entire folded proof and verify that in zero knowledge. So eventually folded schemes become zero knowledge, but initially they are not. So talking about Nova Scotia, I've got the QR for the repository up there. If you have used CirCom at all ever, it would probably take you 15 minutes to get something working. It's an incredibly easy repository to use. Basically, the only thing you need to think about, and I'll show it briefly in a second, is the public inputs, which are just step in and step out. And basically, for some instance n in your chain of the IVC, the step in for n is going to be the step out for n-1. So going into ZK Summit Folded, I'm not going to go over everything that was already talked about, but briefly, you've got the cards, which produce baby jub ECDSA signatures. There's a bunch of different groups. There's speakers, attendees, talks, and these all have Merkle trees. And the base circuit, which we're working from, checks the validity of the signature and then checks the membership of the public key that produced that signature, checks that it's in the tree. So the folded circuit just takes one more step, and essentially at the very beginning we pass in two inputs, which are the tree root. So let's say we're doing the speaker tree, that would be the root of the speaker tree, and num verified, which is always 0 at the start. And as you step through, verifying more and more memberships, you've met more and more speakers in this case, it's going to pipe through the tree root, make sure that you're always using the same tree root every single time. And it's going to make sure that num verified is incrementing once each iteration. And if you know anything about Nova, you're probably wondering why we have num verified. When you're verifying the proof, you have to pass the number of instances folded. And the reason we do that is actually a consequence of the decision to not do full Nova, actually. We clocked Spartan at around 3 minutes to generate a proof, which maybe we were doing something wrong, but even if it was a minute, that's tough to swallow. And not only that, there's also already a large overhead of a public parameters file we need to download. That would double because the verifying key is around the same size. So, and one other thing is that not necessarily applicable to this application, but in a lot of cool ways to use this scheme, it would actually break the IVC to wrap it in the final zero knowledge proof. So if you wanted to continue to build proofs later, you can't really do this. So before I explain that, one other interesting thing, as Enrico mentioned, is that PSI, FHE requires zero knowledge proofs of the correctness of the inputs. As I understand it, the inputs each are one proof. So what we could potentially do and are considering exploring in the future is actually folding all of these proofs of correctness for each of the inputs together and just having a single proof instead of having to do a ton of different proofs to do this. So going back to the decision to skip out on traditional zero knowledge, we actually have proposed with it coming from mostly Barry Whitehat, but us doing a lot of the work and actually messing around with it, something that we're calling a chaff step. And so essentially I'm not going to go into all the specifics, but every single fold is basically taking the current witness that you're trying to fold in, as well as some sort of accumulation of all the previous witnesses. And if we wanted to pass folds between different clients, or we wanted to rely on final folding proof for some reason, that's very unsafe. So the solution is that we are going to mutate our circuit a little bit to actually include a chaff step. And all we're doing here is basically just putting in random data. So in CircCom, what this looks like is we just have a multiplexer which checks if it's a chaff step. And if it is a chaff step, all the constraints that we're doing are just kind of ignored. And all the computation is still done, so we're still getting all of that random witness data. But functionally, we result in this proof that has a witness, a running witness, that is pretty difficult, if not impossible, to meaningfully extract any sort of data from. And this is a little experimental. We have talked to a lot of people, a lot more familiar with folding than ourselves, and no one yet has said, no, you can't do this. But we're not sure yet, so if you have the ability to offer a contrary opinion or even contest what we're saying here, that would be very valuable. So, but consequentially, why would you do this? First off, again, let's say we wanted to retain the IVC property and continue building. We can pass proofs between different clients by doing a chaff step every single time. And that means that even if they know even previous witnesses, they're going to have a very hard time actually figuring out what you did in your iteration of the circuit. We can also use the correctness of the folding proof itself, instead of an actual ZKP to verify our actual computation. And this is still succinct. It's not necessarily as fast as the actual ZKP, but there are a lot of other places where it makes it a lot more expedient, which might make it worth it. And finally, you could even potentially, let's say you really don't want to deal with Spartan, but you still want it, you could use this chaff step to maybe send it out to an untrusted third party who has a lot more computational resources, and verify it there without worrying about them extracting any witness information. So from here on out, it's mostly just kind of focused on the actual application level. Nova Scotia is driven by Rust, so you will need to WASM pack all your code, which is really pretty easy with the library. There's really no issues there. It also is totally compatible with WASM bindgen Rayon, which is super useful. It's basically multi-threading using web workers, and will make your proof at least twice as quick. And another really obvious and intuitive but important thing to think about is that the params file is pretty huge, so you can just chunk it up and compress it and download that a lot quicker. And finally, we wanted to kind of hide away the actual cost of proving from the users. So what we did is we used various different web workers to make it either go in parallel. So in the case of verifying the proofs, there are a couple of proofs and it's all done at the same time. Or maybe more importantly is that as this app is going in the background, you're constantly running folding proofs as you get more signatures in asynchronously. So it's totally possible that you'll get to the end of the app and not have done it all, and in which case you are going to be sitting there, but depending on how much time your user is actually spending in your app, you can get away with hiding a lot of the pain of proving just by putting it underneath. So the conclusions, some good, some bad. First off, there's definitely a high overhead on the data. There's this huge params file, and this caused definitely some issues with accessibility during ZK Summit with limited Wi-Fi and a ton of people trying to hit the Wi-Fi at the same time. It wasn't perfect. And while you're definitely going to get some really quick speeds on any M-series Mac or something like that, poor devices, this computer for instance takes 10 seconds. It kind of sucks. Mobile devices are not great. It takes longer than 2 seconds. But on the other hand, we've also kind of demonstrated that we can recurse with privacy, potentially between multiple clients. And we can do this with Nova, which is pretty primitive in the grand scheme of things, and will get a lot better with other folding schemes. We've demonstrated that we can hide away a lot of the cost of proving just by stuffing it in web workers. And yeah, again, this is pretty easy to, again, so I guess I would say that the window of like tapping and then kind of closing the phone doesn't present a huge opportunity for proving a ton of operations in the background. But for instance, if this was a web app, it would be likely that you would get through pretty much everything in the background, especially if you're not closing the tab or you have something else that you're going into. Your user would probably never notice this. So before I go into the ending thoughts, again, this computer's kind of trash, so I recorded this on MacBook. You're also totally able to go do this on your phone, which I'll talk about in a second, but I'm just gonna run through. So yeah, it's just going through sequentially. Each one of these is a membership circuit. This one's taking a little bit. It'll just go through, fold one membership, fold two memberships, fold three memberships, and memberships. I'm not gonna go through all of it. Get through all of your different proofs that you have. And eventually you're gonna post these proofs. Right now, Nova Scotia doesn't go on chain, but I will talk about CycleFold in a second. And yeah, you can just verify it. The work is pretty similar for the verifier and the prover, honestly. It's still succinct, again, because you're combining a lot of this, but it's not instant. It takes a second. Yeah. So if you have the app and you haven't tried to make a proof yet, you can go into the app, go to proofs, and there's a giant banner right there that you can use. And yeah, it will take a second because you're proving everything from the start potentially. But yeah, definitely worth trying out. The big thing that we're really exploring here is those chaff steps. If those end up being a valid way to construct IBC with privacy, we think that that's going to unlock a lot of use cases where you're kind of recursing between different clients. And finally, this is all done with Nova Scotia, which is a fantastic library, but it isn't quite state-of-the-art at this point. PSC has, I think they just renamed it. It used to be Folding Schemes. But they have a folding repository that has a CIRCOM front end that is like a day away from being merged in. And it also has a Solidity verifier, which is a little bit further out, but gives a lot more functionalities. So if you are interested in messing around with folding, it's only getting easier and easier to use. So it's definitely worth exploring, especially in the coming month. So yeah. That's it. Any questions? Yes.
Do you think it would be worthwhile to explore using WebGL to
Probably,
make it faster?
yeah. This was built on a very short time frame, like a week, maybe a little more. So I guess we did the circuits earlier, but the rest of it, the actual implementation, was all in a week. So I think that would be a very worthwhile endeavor.
Okay, I'd love to talk to you about it.
All right, we'll definitely follow up. Cool. Nope. Okay.
Can I ask a question?
Yeah.
What kind of homogeneity is needed between the different, like, can we extend chaff steps to add more different types of computations? Or do they all have to have some sort of homogeneity beforehand?
They do have to have some kind of, they have to be the same shape, like at least in Nova. I think that there are other ones that allow you to do different shapes. I don't know if that's CCS or what, but specifically with this, you have to have the same kind of circuit. So if you want different things that you're doing, you're basically using a multiplexer, computing all of it and choosing the signal you want. But this is only with Nova, and I think in later schemes you probably could do what you want to do. Yeah.
Cool. Let's give a second round of applause to Jack.